Okay, Chemistry 2341. Welcome to Chapter 7, Part 2, Alkyl Halides and Elimination E2. Okay, so starting from our first slide here, let's move on to what we're going to look at as far as how the alkyl halide substrate affects the reactions, okay? So most of the time, E2 reactions are in competition with SN2 reactions. The better the nucleophile, the more likely it is to do a substitution reaction. So what we want to do is we want to minimize or specify which mechanism we want. And so we have to think about our substrate effects and what other things we can do to get the reaction that we want to happen. So because the SN2 reaction and E2 mechanism is different and how the alkyl halide structure affects the reaction rate, okay? As the number of R groups on a carbon on the leaving group increases, the rate of E2 increases, okay? So in an alkyl halide, a primary alkyl halide, SN2 goes up is faster than on a secondary halide or a tertiary halide. It's the opposite for an E2 reaction. As the number of carbons with hydrogens on them increase, so does the reaction rate. What you can also think of is as you're trying to form a more and more substituted alkene, the reaction rate goes up, because here we would have a terminal alkene, here we might have a internal alkene, and here we might have a tri-substituted alkene. So you can think of them being an opposite and in competition with each other, but primary is faster for SN2 substitution reactions, tertiary is fastest for elimination E2 reactions. Okay, let's go and look at that a little bit more, okay? So, and part of this has to do with the product stability and the rate of these reactions. By increasing the number of R groups on that carbon, the leaving group is more likely to form a more substituted and more stable alkene by the E2 reactions. So let's take a look at this primary reaction. Remember, our primaries probably are not going to go through an E1 mechanism because you'd have to form a carbocation, and the primary carbocations are less likely. Okay, so in an E2 reaction, we have our base coming in and starting to associate with our proton. It's starting to tug on that proton so that it will encourage the reaction to take place. Then the electrons kick in, and that kicks out our bromine. So if we have our primary alkyl halide, we're going to end up with a terminal alkene or a monosubstituted alkene. Monosubstituted alkenes are less stable than di, tri, and tetrasubstituted. So let's look at our tertiary alkyl halide here. And so all three of these methyl groups are equivalent, so it really doesn't matter which one we do. But again, in the E2 mechanism, the first thing that happens is our base comes in and starts to tug on that hydrogen, pull that hydrogen off. Then the electrons kick in, and then our bromine kicks out, giving us our substituted alkene. In this case, it doesn't matter which of those protons we pull off, but we can only form a di-substituted alkene, okay? But this di-substituted alkene is still more stable than a monosubstituted alkene, okay? So we have our thermodynamics are telling us that the tertiary alkyl halide is going to go faster because it forms the more stable intermediate and it forms the more stable product. I'm sorry, the more stable transition state, not intermediate, more stable transition state, which gives us the more stable product. Okay, so now let's start trying to predict the major products for E2 reactions right here. So when more than one product is possible in E2 reaction, you are always going to favor the more stable alkene. And in alkenes, the more stable alkene is the more substituted alkene. So we use a rule, what we call Zaitsevs rule. Zaitsevs rule says the more substituted alkene is obtained when the proton is removed from the beta carbon that is bonded to the fewest hydrogens, okay? So in the case of this compound here, which has the iodine is in the tertiary position right here, so that means we have a choice of having a beta carbon with 2 hydrogens on it here, a beta carbon with 2 hydrogens on it here, and a beta carbon with 3 hydrogens on it here. It will not be the major product for the one with 3 hydrogens on it. because it's going to give the least stable transition state. Therefore, the major product is going to be the one where it removes the one that is already bonded to one carbon or only has the 2 hydrogens on it, making the major product our tri-substituted alkene versus our just di-substituted alkene, okay? So if we think about that as relative reactivities as well, that transition state goes through the same thing where we have the one that'll give us the more substituted alkene is going to give us our product. Therefore, that's why our tertiary halides are faster, because we're going to give a tri-substituted alkene. Our secondary alkyl halides can give us internal or secondary di-substituted alkenes, and our primaries give us our terminal alkenes, because that's one of the few things that's possible. Okay, there is one caveat to Zaitsevs rule, and it says that the more stable alkene is formed in the highest yield. More stable is usually more substituted unless there's the possibility of creating a double bond that's conjugated with another double bond, okay? So if you can form an alternating double bond, single bond, double bond, that is going to be more stable than a double bond, single bond, double bond. So when your 2 double bonds can be conjugated, they will be conjugated. Okay, so let's take a look at that on a couple different substrates here. So if we start with this 4-chloro-5-methyl-hexene, we have the possibility of pulling the hydrogen off this compound or pulling it off this compound, okay? So there are 2 hydrogens on that carbon, and there's 1 hydrogen on this carbon, okay? So by Zaitsevs rule, it says we should be pulling it off this one as our major product. If we do that, we're going to form a methylene in between those 2 double bonds. So we're going to have a double bond, single bond, double bond structure. And if we pull it off the one with the 2 hydrogens over here, we're going to end up with a double bond, single bond, double bond structure, okay? So the idea is we can actually, instead of pulling it off the one with a single hydrogen on it here, it's going to pull it off with 2 hydrogens only because it's going to form that conjugated structure, okay? So let's look at that again. In the presence of benzene, benzene also has double bonds in it, and therefore this will act as wanting to have it conjugated. So we have the choice of pulling it off of this, which has 2 hydrogens, or pulling it off of this, which has 1 hydrogen. And in the case of this, our major product is going to be the one that is going to be in conjugation with the benzene ring. It's going to pull the one off with 2 hydrogens versus the one with just 1 hydrogen and make it non-conjugated. So that's the only caveat I'm going to show you on Zaitsevs rule, is that conjugation is the only thing that will overcome more substitution. Okay, so let's look at Regio selectivity on E2 reactions again. So if we have a substrate like this, we have a nice classical substrate that is a tertiary alkyl halide. And let's look at our conditions here. We're using a polar protic solvent with a strong base. And we're doing it at high heat. We're doing it at about the boiling point of ethanol. Remember, heat encourages elimination reactions, okay? So we have a base and we're heating it to encourage elimination reactions and discourage the substitution reaction, okay? So what we can do is we have the choice of pulling it off this beta carbon, but because that has 3 hydrogens on it, this beta carbon, because it has 3 hydrogen on it, or this beta hydrogen, which has 2 hydrogens on it. Okay, so that means that it's going to, by Zaitsevs rules, take the one with 2 hydrogens on it versus 3 hydrogens, giving us our more substituted alkene as the major product and our less substituted alkene as our minor product. Okay, so Now that is for if we have a small base, ethanol, this ethanol base. If we have a big, huge, bulky base, what happens is that the base cannot come into this side here because imagine it's really big with an anion here. And so it's very difficult for it to come in to get this because of the this group here acting as a steric hindrance and these groups here acting as a hindrance. So what happens instead is when we have a big bulky base like that is that we instead have it come and attack these ones that are sticking out. Okay, so it attacks either one of these that's sticking out here. We're actually going to end up with this less substituted alkene. So notice there's only 2 groups on this alkene right here versus the 3 groups. But it's doing that because this base is so big and fluffy. If you, let's go ahead and draw that base out. We have those 3 methyl groups there. We have that O minus. And remember, those methyl groups each have a hydrogen on them. So they actually take up space. And so that is becoming big and big and bigger. With every hydrogen we add, it becomes bigger and bigger. And so as it compared with our ethanol, which is going to be this right here, this is our alkoxide with ethanol right here. So all 3 of these methyl groups start making it harder and harder for it to attack in this position, and therefore we end up getting these. So when we are looking at our base right here, we want to look at the sterics of our base. Smaller bases will follow the Zaitsevs rule and give us the more substituted product. Bigger bases are going to give us our less substituted material right here. And this tends to follow what we call the Hoffman rule. So once we figured out what kind of base we have, we look at how big it is to determine which way the reaction will go. Okay, so let's look at stereoselectivity as to whether it's going to form a cis or trans isomer here. Okay, so because that double bond is does not rotate, it's going to be fixed into one position or the other when you form that double bond. Okay, so E2 reactions tend to form the more stable stereoisomer, and in most cases, the trans isomer is the most stable product, or the E isomer if you have groups, okay? And the minor one is going to be the cis isomer, and it has everything to do with having the idea that where which hydrogen you pull off here is depending on where these 2 big groups are, which will determine whether you get the E product or the Z product. Okay. So the way we can explain that is by going back to our looking at our Newman projection. And when we look at our Newman projection right here, we want to see that the hydrogen that's going to leave and the halogen that's going to leave during our dehydration should be, if at all possible, in the staggered configuration. You want the base to be pulling your hydrogen off of this side, having those electrons kick down and having these electrons kick out on that side. So energetically, we want our hydrogen to be anti our leaving group. And therefore, if we can at all configure our situation so that happens, we tend to have it where one big group is on one side and one big group is on the other side, which is why we usually get the E configuration, because this is going to be more stable. If we have it such that we have both the groups on the same side, both big groups on the same side right here, we're now looking at a gauche position where the 2 big groups are next to each other, and that's less stable. So the idea here is that we want the 2 big groups to be opposite each other in this transition state right here, and that gives us our more likely to get our trans or E type configuration from E2 reactions. All right, so this is a little more in-depth description here. So when we have the configuration such that you have the, if you have the halogen and the, okay, halogen, and the base on the same side, you're going to have the base come in, these electrons kick in, and the electrons kick out. That's not as favored as if we have the base come in and start to remove the hydrogen, have the electrons kick in and the electrons kick out. So this anti-elimination is favored, and therefore we tend to get our Newman configuration into this configuration. And when we're in that configuration, we want to see where our big groups are. And in all likelihood, our big groups are going to try to be opposite each other in this type of elimination. Okay, so let's look at that with one more way. What if the reaction only has a hydrogen bonded to the carbon, which the hydrogen is going to move? What will the dominant product be? All right, so what we're going to look for is how can we reconfigure the system such that we have the proton that's leaving anti to the halogen that's leaving. So in the case of methoxide, that's a small base. And so it's going to favor Zaitsevs rule. And we have a choice of, we only have, this is the only place the hydrogen can be removed. Notice. So what it's going to want to do is it's going to want to arrange such that the largest group on this side, which is the phenyl group, and the methyl group on that side are the farthest possible away from each other. Okay. And that'll give us an anti-configuration. Now, in this case right here, we have the phenyl group on the same side with this larger group here. So that's going to be less favored system, which means that if we look at this right here is 1, and this is 1 on this side. So this is the E configuration right here. This is on the first priority. This is on the first priority, which makes this the Z configuration. And the E configuration here is the preferred because it gives us this anti-elimination with the two largest groups opposite each other. Okay, so let's take a look at that with another, using the Newman projection again, okay? So if we have a choice of two different hydrogens, so in the previous one, we only had one hydrogen, so that's the one it had to do, and we only had to look at the free rotation of that sigma bond to figure out where things are going. Now, when we have two of them, we have a choice. We want to do the exact same thing. We want to try to get our largest two groups to be anti each other and have a hydrogen anti to our leaving group. So whenever we can form that, we'd like to do that. In this case over here, we have our halogen and our hydrogen anti to each other, but we have our two largest groups closest together. Okay, so that being said, this right here is our lower energy configuration. Therefore, it's going to give us our E isomer. This is a higher energy configuration that would give us our Z isomer, which means our E isomer is going to be favored because of the energy required to get into both of these anti-elimination configurations. Okay, so let's do a couple reactions here and look at it as an example. So in this case right here, we have 2-bromopropane right here. So the probability is we're probably not going to form a lot of this terminal alkene by removing this right here. So we're going to form an internal alkene because it'll give us our more substituted product, okay? So if we look at this right here, we're going to end up with most of our product being this internal alkene with a little bit of our product being the external alkene, okay? Again, this is a small base right here. So now let's kind of confuse the system right here. Oh, look, we have a carbon that's beta to this halogen that has no hydrogens on it, right? So we can't eliminate into that direction. So we have to eliminate over here, okay? So what we're going to do is we're going to try to rearrange this group such that this methyl group has to be as far away from this T-butyl group as possible. So that being said, our major product is going to give the E configuration. because they're going to try to be as far apart as possible, where the minor is going to be the Z configuration, where this T-butyl group and this meth are lining up with each other on the Newman projection. Okay, that ends chapter 7, section 2.